So I will be presenting this very interesting paper. It was published in 2012 in IEEE Requirements Engineering Conference. And the authors of this paper are several professors from various European universities. And as you can see from the title, this paper presents an approach for detecting uncertainty in natural language requirements. I wanted this presentation to be a bit interactive, so I will be asking you some questions during the presentation, so make sure that you listen clearly. So let's start with what is uncertainty, what is speculative language. I will start by an example because I think it's easy to understand from an example. So you can see two sentences here. And I want you to tell me what kind of differences do you see between these sentences. You can write the answers in the chat. So we have sentence A. The vending machine will offer mineral water. And sentence B. It is possible that the vending machine might offer mineral water. So what kind of differences do you think there are, like in terms of linguistics or just maybe in terms of extra words or anything? Yeah, so as I see, Anton has some answer. He says modal verb, so we have this might modal verb. Yeah, so may or may not offer. So it's like we have these two possibilities. Let's wait for other answers. Yeah, so different scenarios are possible. Yeah, so the sentence A, it's like a factual statement. We can see that the author of the statement is like 100% sure that the vending machine will offer mineral water. So it's a really like strong statement. In the sentence B, we have a possibility. Like author is not 100% sure, so he uses this tentative statement to express that what he talks about is just a possibility. And he uses this might and possible, like what Anton wrote. So we call such language speculative language. And speculative language expresses uncertainty or hesitation in a statement. And this is actually a positive thing because if writers didn't have a possibility to express such language, then like they would need to like express it in this like 100% way, which wouldn't be correct because they are really not sure about it. And the use of such language is usually deliberate, like not always, but usually deliberate. For example, when the author is unsure about something and he doesn't want to commit to these factual statements. And in linguistics, use of such language is often called hedging. So it makes this meaning of the sentence more like fuzzy. If you attended the first presentation in the series by Elena, you will remember that she talked about ambiguity. And these two terms, ambiguity and uncertainty, they are pretty similar. So it will be good to like find out what kind of differences are between them. So again, I will ask you, the audience, a question. What do you think is the difference between uncertainty and ambiguity? And we saw this example of sentence with uncertainty, and I will also provide an example with ambiguity. So this is a sentence. I saw someone on a hill with a telescope. So why is it ambiguous? It may not be like clear at first. It is because we have like two possibilities here. The first is that this someone has a telescope, like the one we are looking, or another is that we are looking through a telescope and we see someone on a hill. And like it is not clear from this statement which one is correct. So what do you think is the difference between like, this sentence and this sentence, like in terms of linguistics? Okay, I see some people are writing. Let's wait for it. Like, don't hesitate to write it if you're like not sure. Wrong answers are still welcome. Okay, so we have an answer from Alexandra. Thank you. Ambiguity is when there are several possibilities of what's happening. Uncertainty is when several possible things can happen. Okay, that's an interesting answer. And yeah, I think I understand what Alexandra meant here. So basically, when you have an uncertain statement, like here's the meaning of the sentence. It is like perfectly clear. Like we cannot interpret it differently. But we have these like two possibilities of what might happen. In an ambiguous statement, like the author probably had like one idea of how the statement should have been, but during writing he used this ambiguous language. So when we are reading it, it is not clear which meaning he meant. So I think that's what Alexandra meant. And the reason that I talked about it is that there are different root causes and remediation actions for uncertainty and ambiguity. When we have ambiguity, here we have a question from Rostislav. Do you mean that one is about the subject and the other is about the author? Did you mean about the statement, Rostislav, this C? Yes, so this telescope, it might be with the subject, or like author may be looking through the telescope.
No, I'm trying to figure out the difference. It's not that clear. My assumption is that sometimes you are sure that things are non-deterministic. So you are 100% know what about everything, the subject, but subject is non-deterministic, one case. And another case is when subject is deterministic, but you don't have enough knowledge to know which way it goes on. So that's different, but that's just my assumption.
Yes, that is the correct answer. So like here, author knows which one is correct, but he didn't express it correctly enough so that we also understand it. And so like remediation actions. Now, what do we do if we have if we get this kind of statement in a specification? We can just ask the writer to like explain it for us. Like, hi, I was reading your statement, and which one did you mean? But in case of uncertainty, the root cause is that author himself was not sure about this functionality. So in this case, we cannot just ask him like what is correct. In this case, we should analyze why there was uncertainty in the first place. Because if author is not certain about the functionality, it may mean that we get a system that doesn't meet users' expectations, and we obviously don't want that. So that is the main reason why we should analyze uncertainty, and I think it can help find problematic areas in the specifications. Now, if we if we again look at the difference, we will see that we have. Let me get the pointer. So we have these words, might and possible, and these are the words that convey uncertainty in the statement. And we call them uncertainty cues. So these are some words that trigger uncertainty in the sentence. And they can help us identify sentences that are uncertain. However, these uncertainty cues on themselves, they are not enough for identifying uncertainty. We should also look at linguistic context, or what I mean with that is that we should look at like, surrounding words as well. For example, here we have another two sentences. Sentence A, the system shall allow an operator to assign colors for countries that appear on the tactical display. And sentence B, it appears that insulin should be delivered in circumstances where the level is likely to go outside this range. So which one do you think is uncertain statement? Only one of them is. So in the first sentence, we just have like this appear. These countries appear. So we don't have any uncertainty here. And yes, Daria, that is the correct answer. Here we have it in a like different context. It appears that insulin should be delivered. So it means that there is some kind of uncertainty. It is not a strong uncertainty, but still we have a little bit of uncertainty here, like whether or not the insulin should be delivered or not. And so what I was trying to say with that is that analyzing uncertainty is not as simple as just like looking for uncertainty cues. We should also look at some grammatical relations and in like what kind of word sense this uncertainty cue appears. And also these uncertainty cues have a scope. So like scope specifies what part of the sentence is speculative. For example, in this sentence, the text interface will provide equivalent functionality, but will likely require additional server requests to perform the same task. So here, only the second part is uncertain. The first part, the text interface will provide equivalent functionality. It is like perfectly certain. It doesn't convey any uncertainty. And authors also devised a strategy of how to identify the scope as well. And this will be like second stage of their approach. I think it's enough about uncertainty. I think it should be clear by now what uncertainty means. So we can now move to like specifics of how the authors implemented this automatic detection. So first of all, the data set. They actually use two different data sets. One is called bioscope corpus, and it is a publicly available data set for research purposes. And it also comes with annotation guidelines, which is also publicly available. So I think that's a good thing because we could potentially use these guidelines as well. And it contains several medical and biological texts annotated for negation, speculation, and linguistic scopes. So we're not interested in negation in this presentation, but it's good that it has speculation and scope as well. And the guidelines also tell us how to also mark the scope. And it was annotated by 3 different linguists. One was an expert linguist who did these guidelines, and then the other linguists followed these guidelines and annotated this data set. And they also used another data set, which they annotated themselves. It is a set of 11 requirements documents from Requirements Engineering Laboratory at Sydney. And it is a more it contains a variety of domains, not just medical text like it was before. It includes transportation, engineering, web applications, communication. And they annotated both uncertainty queues and the scopes, and they followed the bioscope guidelines. And here we can see these are different categories of uncertainty queues. And we can see that we have uncertainty queues in almost all parts of speech. So we have many different ways of expressing uncertainty. Okay, so the authors had 2 different stages for detection. The first one was identifying uncertainty queues in sentences. And of course, it's not just identifying all the queues, but identifies queues that really convey uncertainty. And they also had a second stage where they identified the part of the sentence which was uncertain, so uncertainty scope. And for that, they labeled, for the first stage, they labeled each word in the dataset using the so-called bio scheme. So it is it's general scheme, many people use it. And it works like that. We have 3 different kinds of labels, B, I, and O. So it's called bio scheme. B means that it is a beginning of a queue. I means it is inside the queue. And O means it is outside the queue. So it's not an uncertainty queue. So let's look at the example. So for example, we have this sentence. Tasks may have many milestones which may or may not be associated with the task. So here we have 2 different uncertainty queues. We have may here, and we also have may or may not. This is actually a whole phrase. So uncertainty queues may not just be words, but they can also be whole phrases. And you can ignore this middle part for now. I will talk about that. And basically here is this annotated queues. So may is classified as B, so it's the beginning of a queue, and it ends there as well. And we have may or may not be, may or may not. B is not part of it. So it's beginning, and then these are inside. So why do we need this B as well? So if we had 2 adjacent uncertainty queues, then this gives a possibility to separate them. So if we only had I's, then they would be combined into one queue. And if the sentence contains even 1 queues, it is labeled as speculative at this stage. And So basically, this is our target variable. So this is what we are trying to predict. Like, we want our model to give us this. Is it B, is it I, or is it O? Now we like, what kind of features did the authors use for training the model? So they extracted a variety of features, and we have 4 categories. The first is word token features, and it contains lemma, part of speech tag, and a chunk tag. So lemma is just like the base part of the word. Like, if we remove any prefixes or like postfixes, part of speech tag is at what part of speech is this like word. For example, here we have noun. Here we have like modal verb. So like, it gives us idea of like what kind of in what kind of word sense this word appears, and this obviously has so like it depends on what kind of word sense the word is, if we want to find out if it's uncertain or not. And the chunk tag. So chunk tag basically chunking is a process where we group like different words into groups, or we call it phrases, and this can help us find out what part in what part of the sentence the word appears. For example, tasks. It is a part of noun phrase. May have. It is a part of verb phrase. So again, it gives us some additional information. And they use Genia tagger for that, for extracting these features. They also use basically they reuse this lemma in part of speech tag, but like for each word, they also add lemma in part of speech tag of 3 neighboring words before and after. So it provides some like contextual information. And we also have dependency relation features, which is here, this beautiful graph here. And it shows like what kind of do you also see it, like, it's zoomed? Because it's a bit small.
Larger.
Yeah, so it shows us what kind of relationship there exists between words. For example, here we have this verb have, and here we can see that these tasks, it is a subject to this verb, and milestones, this is an object to this verb. And we, for example, many milestones, this is a modifier to the milestones. So it provides us with a very good contextual information. And actually, addition of this feature greatly increased the accuracy of the model. And we also have another feature, co-occurrence feature. So when we have some cues, when they appear together, they act as like stronger cue. And we had that in this first slide here. So possible and might. So for example, when these two appear together, we can be more sure that they convey uncertainty. So they also use this as a feature. So this will be like marked that it's true they are co-occurring. And so this is like whole training data for classifier. We have all the features, and our target variable is the cues that we are trying to find. So now I think this is, for me, was the most interesting part. Like, what kind of model did they use? They approach this problem as a token level sequence labeling task. And what does it mean? We have a set of input variables, M variables, which are these words in the sequence. And we are trying to predict some target variables, which are in our case this bio tags. Example of sequence labeling task is part of speech tagging, for example. Like we have a sentence, I play basketball, and we want to get pronoun, verb, noun. And like the simple way we could approach it is to break it up in like several classification tasks. So like we would find out probabilities of each of these words separately. And so, for example, this kind of model, it would learn that the word play in like 90% of the cases, it appears as a verb. So it will like learn that it's a verb. So when it will look at this sentence, it will classify it as a verb as well. So like with this sentence, it will probably do kind of okay. But let's suppose we have a different sentence. For example, like I watched a play. And in this case, play is a noun. It is like a theater play. Let's see this example. Yeah, so I watched the play. And here it should be noun. But our like simple naive model cannot know that because it doesn't look at the context. So we want to have some different kind of models that also looked at the context. And authors used an algorithm called conditional random fields. It is a type of sequential model. It is similar to Markov models, if you're familiar with that. They are all sequential models. And basically what's the difference between the previous models that I explained is that these also include probabilities of one state, one label transitioning to the next. So, for example, in the case of part of speech tag, it will mean that it also asks a question like, what is the probability of noun coming after a determiner? So in this case, it would first, like it would, like if we try to like follow the thinking process of this algorithm, it would first think that play, like it is likely a verb. However, here we have a determiner before, and it is like highly unlikely that verb follows determiner. So it should be a noun. So it would like correctly identify this sentence. And I showed this example with part of speech tagging because it's like easy to understand, and also it's very similar to the problems that we have of like classifying the sentences as the tokens as uncertain or not. And so this model would also work good on this task. And I will show you the results in the end. So this is about the first stage, and stage 2 is shorter. So the presentation will be finished soon. And this stage is about uncertainty scope resolution. So finding the scope. And authors developed some heuristics. Heuristics basically means that it is not a statistical model, like for example, conditional random fields, but it's rather like handcrafted rules, just some manual algorithms for finding it. And they followed biscope guidelines for that. And I will not go into detail, but I will just like show you example of a rule. In this case, it's a rule for auxiliaries. Auxiliaries are words that may, might, and so on. So if the main verb is active, then the scope starts with the auxiliary and all its dependents. So here it's the example of of a sentence with active verb, and we only mark the second part as uncertain. If the main verb is passive, then the scope includes the subject argument that appears in the preceding text. So here, the word function is a subject argument, so it is also included. And for this algorithm, they used dependency parse information, which is the same as this dependency relation features. And they used Stanford parser for that. You may be familiar with Stanza. Stanza is just Stanford parser, but like ported to Python. And now we reach the end of the presentation, and here are the results. For stage 2, these results are by performing tenfold cross-validation on their manually annotated dataset, the second dataset. Cross-validation just means that they used same part of the same dataset, both for training and testing. And it is usually used when this dataset is not very big, and we don't want to like waste some of it on testing. And as you see, they got pretty good results. They have F-score of 85. But however, the results are not as good for this stage 2 of scope resolution. They got like 61%, but this is like without stage 1, like only identifying scope on the annotated queues. And for predicting queues, like for stage 1 following stage 2, they have like pretty low percentage, 52. However, I think this first stage is more important because it shows us like it marks the sentences as uncertain or not uncertain, and then like people can look into it and see like what kind of problems there are. That is all with the presentation. I think that there is a possibility of us like using this this algorithm presented, like mainly the first part. The main problem that I see is the data set, because only this first data set is available publicly, and it is like very domain specific. It just contains medical and biological tests. So like we would probably need to annotate these uncertainties ourselves if we want to like create similar predictor. So thank you very much for listening. I hope it was interesting.